Yeah, I would say the first one, but technically kind of the first three. Because what's the only difference between the first one, the second, and the third? This one has a u instead of, it's a composition of functions, it's chain rule. And so since it's chain rule, bunnies multiply, you have the regular rule, 1 over u times u prime. But where did all these come from again? Once again, this is forever card number 14. Did you guys back me up on that number? Does that sound right? Okay, so for forever number 14, let's go back a page. Where did it come from? In pre-cal, we talked about a change of base formula, and a change of base formula says, hey, guess what? You can take any log of any base, and you can convert it to any other log of any other base. Formula, putting the argument on the old base on bottom. But we're not going to change some weird from log base 17 to log base 2. Who cares about that? We like LNs. But check it. We can rewrite change of base formula to be 1 over ln of b times ln of x, and this is just a constant. And what do we do in derivatives with any constant? We multiply. Constant multiple rule. And so, when you guys look at your card, when we get down to log base b of x or log base b of u, you guys should know these are basically the same thing, just this has a composition inside. We can think about log base b of x as 1 over ln of b times ln of x, whose derivative is 1 over x. And so if it helps, I don't know if it helps, maybe for some of you, if it helps, you could technically memorize that log base b of x is just 1 over ln of b times ln of x. But for some of you, it's a bit harder to remember this is a constant, and so you would just keep it and then do the derivative of ln of x, which is 1 over x. But if it does help some of you, that's technically what's going on. The constant stays, constant multiple. The derivative is 1 over x. So what I need you guys to realize is that the derivative of log of any base starts off being just like an ln, 1 over x, ln of b. You just need that extra little ln of b for the change of base formula to make everything legal. And so same thing down here, we could rewrite this to be 1 over ln of b times ln of u, which derives to be 1 over u times u prime, times that little extra constant. But you can think of it as it's the exact same thing as ln of u. Logarithms have the exact same pattern of 1 over x or 1 over u. Just whenever you have a log base, you need ln of b. Or as we're going to say a little bit later, lambda. So 1 over u, lambda, with u prime. But let's practice it. Let's practice it. Now, I'm going to technically rewrite this puppy first, okay? I'm going to rewrite him first. We're going to do one other example in a second. But you don't need to rewrite him every time. I'm just trying to show you that you can rewrite him. You can go ahead and say this is the exact same thing, 17 log base 3 of x, which is not an ln, but it's close. Am I saying it's close? What does ln have as a base? E is a number? Yeah, 2.71828, so it's close, give or take. But it is different. So to make it all precise, check it. I could make this 17 ln of x over ln of 3. Totally legal from the change of base formula, which I could rewrite as 17 over ln of 3 to ln of x. Because ln of 3, you could plug it in your calculator, it is a number. That's what I mean by change of base formula, ln of b is always a constant. It's always a constant. I need it, it's important, because it's the conversion from one to the other. And so we could go ahead and derive this now that it's rewritten and say, okay, f prime of x is equal to constant multiple, keep the 17 over ln of 3, and take the derivative of ln of x, 1 over x. But check your rule in your forever card. Isn't it the exact same thing as if I was to constant multiple, keep the 17 and do 1 over x ln of... So if you memorize the rule, you can jump right here. If you don't memorize the rule, you have to remember your change of base formula and the fact that ln of b, ln of 3 in this case, will always be a constant. So you guys, take it away. What if I was to give you f of x is equal to, let's not make it too hard, huh? What if I was just to do something like 5 log base 5? That's okay. of 3x squared. Okay, go. You can either rewrite or you can try to go straight to the rule. Either one's fine. You can either try to rewrite or you can go straight to the rule. Either one's fine. Some of you guys have already practiced the rule, which is really nice. All right, check in your groups. See if you guys agree. I'm going to use the rule, but you guys could have rewritten. You guys just check really quietly. I didn't hear anyone talk. You guys agree? Take a couple seconds, just applying a new rule. You guys can do it. Okay, that's not for you guys. So, what formula did you guys use if you used a formula? This is awkward. What formula did you use if you used a formula? If you went straight to the derivative, what formula did you use? Quadratic formula? Okay, I was like, huh? Yeah, log B of u, right? It has to be a chain rule because what's inside? Yeah. So you could think of the outer being 5 log base 5 of u, and the inner being 3x squared. But it's just a u, right? Just an f and a u. There's not like an f and a u and a v, not like an f and a g and a h. So technically, we just need a u prime. So you could have rewritten this, and I'll show that in just a second, or you could have gone straight to the derivative rule and said, hey, no idea. Constant multiple, keep the 5. Okay, log base b of u. The derivative is, pretend it's an ln for a second. Wouldn't it be 1 over u? Oh, wait, but it's not an ln. Okay. I need ln of 5 to offset times u prime, which would have ended up being, we would have simplified a little bit, 30x all over 3x squared ln of 5. The x's can reduce, 1 from the bottom, the whole 1 from the top. The 3 and the 30 can reduce. And our final answer would be 10 over x ln of 5. But you could have also gotten there if you had rewritten this using the change of base formula to be 5 ln of 3x squared all over ln of 5, which you could have made 5 over ln of 5. That's just a constant times ln of 3x squared. Because then you would have had your 5 over ln of 5. Oh, there he is, 5 over ln of 5 times derivative of ln of u is 1 over u times u prime. 1 over u times u prime. And I'm thinking, guys, we're doing okay for the u in the sense of, can you guys do the mental math on 3x squared's derivative, right? Just 6x. That one's not too bad. Some u primes are messy, so you would have wanted to actually write it out and take some time on the u prime, but I figured we could mental math u prime on this guy to be 6x. We good? Give me a thumbs up if you say yeah. How many of you guys went straight to f prime equals with the rule? Give me a thumbs up or a raise. How many of you guys tried the change of base instead? Okay, it's like half and half. Long story short, you just need a way that sticks in your brain. I am making you guys memorize the rules because ultimately, it's going to be necessary to memorize, but using change of base does allow your brains to kind of have a concrete reason as to what we're doing, why we're doing it. So that might make it more memorable for some of you. Write him down. Don't worry, I won't even make you or let you tackle this one alone. But write this one down, and I want you to ask yourselves the question as you write it, what makes it so much worse? Maybe. That's just like one part of it. What makes it so much worse? The sine, what else? The sine cubed, what else? There's an f, technically, f of g of h. But what else do you have? Inside a product rule. Anyway. What's the big picture? The big picture, skip a couple lines. The big picture, or just don't write it yet, is it's an ln of u. Oh, well, that's not too bad. It's 1 over u. Right? Just rewrite it. But what's the struggle? Do you see how this is a 1? This is 1? Where I might want to go ahead and do the u prime off to the side first. Okay, so I'm going to go ahead and rewrite the u, and let's see if this makes sense. I have 3x squared times sine of 2x cubed. Why did I rewrite? Don't get tricked by the... I didn't make you guys repeat it on Friday or on Thursday or whatever day I taught it. That's why you don't remember. Don't get tricked by the notation. And then you're supposed to say, I won't get tricked by the trig notation. Okay? We're going to actually do this. Ready? Don't get, not too bad. Don't get tricked by the trig notation. Okay, that was fairly good. Period 6 had you beat their first time too. Come back. I won't get tricked. That's funny. Don't get tricked by the trig notation. No, that's not your part. Try again. Try again. It's the same thing I did. No, same thing I did. Same thing I did. Okay, it was my bad. It was my bad. Don't get tricked by the trig notation. We'll keep working on it. Okay, why am I saying that? Our brains will think this is the outer every time, unless we remember that this is just trig notation for the whole sign being raised to the third power. Okay? Our brains are going to get tricked as to who's the outer matryoshka, who's the f, every time, unless we remember the trig notation of whenever there's a cubed in by the sign, it's the whole thing cubed. Now that's just the beginning. We just rewrote u. Now what? What's the big picture? Product rule. For what? For u prime. Okay, so u prime. Nice thing is, second, we just have to rewrite them. Okay, well, I can do that. We have sine 2x cubed. Second d first. I can do him 6x plus first. Just rewrite. Okay. Need you guys to mentally kind of stretch it out a little bit. You ready? No? Okay. If I was to take this little triangle off to the side, and if it helps some of you, you can totally just come over here and say, who's triangle prime? You can even separate it down even more and say, okay, I'm scared, so let's write it down. Triangle prime, how are we going to do that? Well, who's triangle? Sine of 2x cubed. Okay? Couldn't we technically break triangle down? And couldn't we say f is equal to u cubed, u is equal to sine of v, and v is equal to 2x? You guys agreeing with the pieces in that chain rule? I have something cubed, I have sine of something, and I have the something. There's my f, there's my g, there's my h. Remember, how do matryoshkas work? Derive the outer, keeping the inner. So derive the outer. Oh, what's the derivative of this? Good, 3u squared. What's the derivative of this guy? Cosine v. What's the derivative of this guy? 2. So what does that end up being? Well, hold on, we have to rewrite them, right? But can we rewrite them? 2 times 3 would be 6 times who squared? U squared, which is sine of v squared, cosine of v. Wait, who's v? Oh, so it's sine of 2x squared times cosine of 2x. Got it. Or if some of you want to think about it, derive the outer, bring down the 3, make it a 2. 3 sine of 2x squared Then peel off the cubed. Next layer, derive the sine, cosine of 2x. Peel off the last layer. Now we just have the 2x. Derivative is 2. The 2 and 3 become 6. Is that what we should plug in here? It's going to throw you off. I know, it was green, so now I'm going to black. What am I trying to show? Uh-oh, that wasn't even a good showing. What should we look for? Like terms. Are there any like terms?
2x.
How many sine 2x's? So we can take out a squared. Isn't there also a 6x? Yeah, we could do that. So we could go ahead and pull out a 6x. We could pull out a sine squared of 2x. Ooh, I'm going back to the notation from each of the terms. The 6x is gone. One of the sine 2x's is gone. There's a sine 2x left, plus, okay, who's left of the second guy? I took away the 6. I took away 1x. We have a 3x left, right? And then both of those signs are gone. That's nasty. Oh, wait. What can we do? The 3 reduces with the 6. One of the x's reduces. And then 2 of the signs reduce. And so I believe you guys can double check me. It sure looks like what we have left is a 2 on top with the sine 2x plus 3x cosine 2x all over x sine of 2x. And anybody who wants to reduce further, you're going to kill a kitten. That numerator, that denominator does not match in any way, shape, or form. AJ? Nope. Because remember, the derivative of ln of u is 1 over u times u prime. No ln in the answer. Now, was that impossible? No. Was it hard? Yes. So I wonder if there might be another way to do this using pre-cal. Using pre-cal, logarithmic differentiation. Another process of differentiating, simplifying functions with log properties before deriving, aka rewriting. You guys know what I mean by rewriting, right? With pre-cal log properties first. Logarithmic differentiation. Basically, it's a snazzy way of saying rewriting with pre-cal log properties first. If there's an ln, go straight for it. If there's not an ln, put in an ln. What? Why would I put in an ln? Well, we're not going to be able to totally do that yet until we learn something called implicit differentiation. But for right now, if there's an ln, we can use pre-cal to help us. And let's see if it does truly help. Hey guys, go look at the pre-cal properties to logs as soon as you have this. That's the very first page of section 2.4b. We wrote about all sorts of pre-cal stuff, including a product property, a quotient property. I didn't name them. A power property of logarithms, pre-cal properties. A product property, a quotient property, a power property. I didn't name them. Pre-cal properties. I'm about to do some crazy voodoo stuff on this function, but it's not going to be crazy or voodoo. It's going to look like it. I need you to go look at those pre-cal properties. The product property, number 2, the quotient property, number 3, and the power property, number 4. The properties of logarithms on the very beginning of 2.4b. You guys looking at them? I'm about to have some fun. Okay? Rewrite. I can rewrite this guy. Rewrite, not deriving. To be ln of 3 plus 2 ln of x plus 3 ln sine of 2x. Just rewriting. Do you understand why? Every time there's a times in ln's, in a single ln, what can you make it? Addition. Every time there's times. You guys see it? ln of pq is equal to ln of p plus ln of q. I used that property, but I also used ln of x to the n is equal to n ln of x. I used the power property of bringing down a power, but I also used the product property of changing it to a sum. So every time there was a times, I was able to make plus a new ln. Every time there was a power, so technically you can think of it as it was ln of 3 plus ln of x squared plus ln of sine 2x cubed. I brought 2 down to 3. Now why on earth was that awesome? How do I derive this? Hey guys, what's the derivative of any constant? 0. But if you don't believe me, what's the derivative of ln of u? 1 over u times, what's u prime? What's 3 prime? So however you do it, that's going to go to 0. It's just a constant. It's a number. Plus, what's the derivative of ln of x? 1 over x. Plus, what's the derivative of ln of u? Ugh. That one would have been a little bit harder. But the derivative of ln of u is 1 over u times u prime. That's a little outer inner sine of u, so I can make that cosine. So I had to do my 1 over u times the derivative of u prime, derivative of sine 2x. Sine of v would be cosine of v times v prime. And we end up with 2 over x plus 6 cosine 2x all over sine of 2x. Wait a minute, we're in trouble. Or are we? How could I make this one look like this one, or make that one look like this one? Either multiply to get common denominators, or break it apart, right? Because if I was to break it apart, just for instance, couldn't I take this one over here, and couldn't I make it 2 sine 2x all over x sine 2x plus 6x cosine 2x all over x sine 2x? Check it, the signs reduce, check it, the x's reduce, and it's the exact same thing. Which one, mathematically speaking, as far as taxing on your brain, seemed easier? Derivative rules, probably this one. As far as like just following the calculus flow of things, probably this one. It just kind of depends. Which one would you make more mistakes on? I don't know. The nice thing is in homework, those of you guys that kept on going in 2.4b, don't they tell you to use logarithmic differentiation sometimes? So in the directions, it should say use logarithmic differentiation. They're giving you a hint saying, hey, those log properties are a good idea. Does that kind of make sense? Okay. That might take a little bit of practice, but let's keep going because we still need to get to exponential functions. This one, kiddos, don't really write it down. I'm just trying to show you in the future logarithmic differentiation can be used for something else. We just don't quite know enough to go straight there. But long story short, you don't need to write this down at all, but we can take a nasty, nasty, nasty chain rule problem, and we could actually take ln of both sides. For our rewriting, still no derivative is taking place. But maybe some of you guys can notice how, ooh, if I could put an ln in, and if I can figure out how to take a derivative of something like that, maybe I could make some harder chain rule problems easier. But we need to learn something called implicit differentiation, which actually says something to the effect of how do we take derivatives with y's, and we're not there yet. That's going to be chapter 2b. So don't stress about that. If you do see anything where it says use logarithmic differentiation, not that any of you guys are like using AP practice books right now, but sometimes you'll see logarithmic differentiation and there is no ln yet. We're allowed to put in an ln, just you guys aren't quite ready for that step. So let's keep going to exponential. Trying to keep it basic. Doesn't mean easy, but there's one more set of basic rules that we need to get through, and those are exponential derivatives. So, general form, we're going to pre-cal again, just like we did with logs. We're going to pre-cal again, just like we did with logs. You guys know e to the x, hopefully. Swoop, there he is. So what's the difference between b to the x and b to the u? Not much. Not much. Just like with e to the x, The y-intercept of any exponential function non-transformed is going to be 0, 1, because anything to the 0 power, any positive base to the 0 power is 1. Technically, depending on what b is, that point can change, but we still have a horizontal asymptote at x equals 0. No vertical asymptote, it just keeps on increasing forever and ever. We could talk about limits. As we go to infinity, b to the x is going to go to infinity. It swoops really high. It actually goes higher and higher depending on the base, if the base gets higher. As you go to a negative infinity, there's that horizontal asymptote, so it goes to 0. And we already know the basic rule. What's the derivative of e to the x? Just e to the x. The derivative of e to the x is just e to the x. When we learn that thing called implicit differentiation, we'll see why the derivative is what it is. But for right now, you guys have already memorized it. You know that the derivative of e to the x is itself. But the problem is, just like with logs, e to the x is not the only exponential function. Ah, bummer. So what do we do if we're given b to the x? What do we do if we're given b to the x? Well, here's the crazy thing. I'm going to kind of have to cheat and show you the implicit differentiation. I'm going to kind of have to cheat to show you the implicit differentiation to make this possible. But the nice thing is you're not necessarily required to do implicit yet. I'm going to kind of cheat and show you the implicit differentiation, okay? So what if I was to take ln of both sides? If I was to take ln of both sides, I could bring that little x down, and I would have ln of y is equal to x times ln of b. Technically, I could rewrite this to be like ln of b because that's a constant times x. But the struggle is I don't need to stop there. I need a derivative. I can't stop there. I need a derivative. So here's the crazy thing about derivatives. You can take them whether they're y's or x's. The only struggle is if my function starts off with x's, I take a derivative just like normal, which would end up being the constant multiple rule, times derivative of x is 1. But over here, where I have the y's, I still use my rule of 1 over y. 1 over u times u prime. But what's y's prime? 1? No. Y prime is dy dx. So then it starts to get a little bit confusing. And once again, you might not understand everything going on, but I'm just giving you a peek at this thing called implicit differentiation. Taking the derivative of variables that are not the same, or expressions that are not in terms of the same variable. But I can get my dy dx by multiplying y on the other side, and here's where it gets a little crazy. We wouldn't stop there. Just like if we have u's, if we have v's, we always have to substitute back in. I'm going to substitute back in who y was. But we have to come back here and say, who was y? He was b to the x. And if you guys notice, this looks a lot like the derivative of e to the x, which is itself. Except whenever you have a base that's other than e, just like with ln's and logs, whenever you have a base that's other than e, you still have the derivative of b to the x being b to the x, but what else do you have with it? ln of b, just like logarithms. Now, the fun thing is I actually have a way of remembering this one. But with both log base b and b to the x, whenever your bases are something other than e, oh, we like e, they're easy. Derivative of ln is 1 over x. Derivative of e to the x is e to the x, right? Derivative of e to the u times u prime. All you got to do is multiply. Chain rule, u prime. B to the x. It's harder, but pause. It's so similar. Derivative of e to the x is e to the x. Derivative of e to the u is e to the u times u prime. Derivative of b to the x is b to the x times something extra. Derivative of b to the u is b to the u times something extra times u prime. Look, they're so close. But there's a b instead of an e. And so what do you need every time there's a b instead of an e? An ln of b. And here's the silliness. Here's the silliness. The derivative of boo is boolim. The derivative of boo is boolim, boo prime. Silly, I know. It's a few years back. Someone just thought of it. I have no idea. Like a boolim boo, and then we had a robot on the sweatshirt. I have no idea. Sweatshirt, we need to do those design ideas this week. Get some extra credit too. Boolimbu. Boolimbu. But here's the idea. Anytime you have a base other than e for ln's or for e to the x's, the rules are exactly the same. They just need this little extra limb in there. Derivative of e to the x is e to the x. Derivative of b to the x is b to the x, ln the b. Derivative of e to the u is e to the u times u prime. Derivative of b to the u is b to the u times ln the b times u prime. Forever number 15. So let's check it. What's going on? What if you have the derivative of 2 to the x? It's an exponential. He's nice. He stays the same, except it's not just 2 to the x, but that's the beginning. Derivative of 2 to the x is 2 to the x. Ah, it's a 2, not an e. So what do I need? ln of 2. Check it. The rule. Derivative of e to the x is e to the x. Derivative of 2 to the x is 2 to the x, ln of 2. We can think boolimbu. Derivative of b to the u is b to the u, ln of b times, well, u prime, x prime is just 1. Dun, 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 dun. There's not really enough way of writing that. Now I went to e's. I know, but I wanted you guys to make sure that you knew what was going on with e's. Because the e's are going to get a little bit harder if you guys haven't noticed yet. Because now we have u's in there. But don't worry. Whenever you have a u, just remember u prime. Sorry. We're not doing integrals. We're doing derivatives. U prime is equal to 2x. Derivative of e to the u is e to the u. U prime. So two new things are going to happen. Now you have e to the u's that need u primes, and now you might have b to the x's or b to the u's that need an extra little ln of b. But otherwise, they're going to follow along in e to the x's. Same pattern of deriving. Ugh. But what about this? This is nasty. This is a quotient rule. Nice thing about exponentials. If you have like bases, aren't there sometimes some pre-calc properties that'll help you with them too? So his derivative without doing quotient rule, I don't like quotient rule, do you? Is e to the u times u prime. So what am I trying to show you? Is pre-calc coming back a little bit? A little bit. But is there still some calculus formulas that we should memorize to make life easier? Definitely. What do we do with log base b of u? Treat it like ln. 1 over u, ln the b. U prime. What do we do with derivative of b to the u? Treat it like e to the u. b to the u, ln the b times u prime. Guys, practice your new rules. This is the end of section 2.4b. Let's see how we do on homework tomorrow. We'll grade, check on comprehension, understanding. Study those forevers. Quiz not until Wednesday. Bye, guys. I know. A lot got put in. You guys need to put in the time to practice.